In the next 20 minutes, I'm going to do something almost nobody on YouTube does: explain fire at the electron-orbital level, without a single equation, and without lying to you about what we still don't know. By the end, you'll look at any flame on Earth and tell, in one sentence, why it's that color, why it needs that much heat to start, and why, physically, you yourself are a slow version of it, running at 100 watts, right now, every second. Receipts on screen every 90 seconds. Honest, where the physics is still arguing. What you just saw on screen isn't chemistry. It's a quantum decision, 180 years in the making, and James Joule wrote the very first receipt for it in 1841. Let's go. By the time you turn 10, you've probably seen fire 1,000 times. Your birthday candles. A gas stove clicking on. The wick on a campfire catching at the third match. 1,000 times. Easy. And almost none of us, I include myself in this, have ever stopped and asked the actual question. Not, how do you start one? Not, what does it need? But, why does this even work? Why is this an option the universe gives us at all? The sun is just a really, really slow fire. Same family. Same physics. 2 layers down. Different scale. We'll come back to that. Here's the part school skipped. Paper needs a match. The sun does not. A log will sit on your living room floor for a decade and never ignite at room temperature, but iron filings, in pure oxygen, will burn from a single spark. A wet fingertip held half an inch, about 1 centimeter, from a candle flame doesn't burn. Move it half a centimeter further in, and it absolutely does. Don't try that one yet, by the way. We'll get there. Different rules for different fires? Or one rule? 3 layers deep, and we've only ever been shown the top one? Richard Feynman opened his physics lectures with a sentence about atoms. The very next thing he talked about was a candle. He knew exactly which question was hiding underneath the school answer. For the next 18 minutes, that's the question we're going to follow down. Okay, before we go anywhere weird, give school its fair hearing. Because the answer your chemistry teacher gave you, fuel, oxygen, heat, is actually right. It's just right, the way water is wet, is right when you're 4. Here's the picture Feynman himself liked. Imagine a ball sitting in a little dip. Off to its right, much lower, there's a deep valley. That valley is the stable end-state carbon dioxide, water vapor, lower energy. The molecules inside your wood, your paper, your natural gas, they already want to roll into that valley. They just can't, because there's a hump in the way. That hump has a number. For the kind of hydrocarbons in everyday fires, the molecules in candle wax, in pine, in methane, it sits somewhere between 200 and 400 kilojoules per mole. That's the activation energy. That's the cover charge to get into the room where fire happens. A match, a spark, a flame, already going next to it. All those things are doing the same job, giving the ball one good shove. One kick hard enough to clear the hump. After that, the molecule rolls down on its own, and the energy it releases on the way down is bigger than the kick it took to get over the top. That's why a fire, once you start it, keeps itself going. It's paying its own cover charge from then on. Now, and this matters, this picture is right. It's the school answer, and it isn't a lie. It explains how a fire propagates. What it does not explain, what no chemistry teacher I ever had explained, is why the hill exists at all. And the second you ask that question, the second you ask why the hill exists at all, chemistry has, very quietly, handed you back over to physics. Without telling you. That's where we go next. So why is the hill there? The school answer told us how high it is. 200 to 400 kilojoules per mole, depending on the fuel. What the school answer never tells us is what the hill is actually made of. It's not made of heat. Heat is the thing you use to climb it. The hill itself? The hill is made of something much weirder. It's made of electrons that don't want to let go. Take the most common bond inside almost everything you've ever set fire to: wood, candle wax, paper, natural gas. A single carbon atom holding onto a single hydrogen atom. That handshake, on average, is worth about 413 kilojoules of energy per mole of bonds. That's the price of admission. That's one tiny piece of the hill. Multiply that by the trillions of those handshakes inside one matchstick's worth of wax, and the hump in front of you suddenly stops being a metaphor. It's a wall of refusal, atom by atom, electron by electron. The match isn't bringing heat to the wax. The match is bribing the electrons to let go. And once you say it like that, once you admit the hill is just how stubborn a bunch of electrons are, you're not really doing chemistry anymore. You're doing physics. Quietly. without anyone telling you. Which raises the next question, doesn't it? Where did these electrons get the energy in the first place? Why are they sitting in this dip at all? Who put them there? Think of it this way. Imagine a parking garage. Top floor still has cars on it, and right above that, one floor up, totally empty. Hold that picture for 15 seconds, because that picture is fire. Hold the garage in your head, top floor full of parked cars. The floor right above it totally empty. The cars are not happy on the top floor. They're tired. They've been there a long time. They would, if they could, find any way to get down to the ground floor where it's quieter, lower, more stable. But they can't. Not without help. Not without something giving them a small push up to that empty floor above first, where suddenly there's room to move, room to slide, room to fall all the way down. That parking garage is an atom, or, more precisely, it's a molecule's last electrons. Chemists have names for those two floors. They call the top floor with the cars on it the HOMO, the highest occupied molecular orbital. They call the empty floor right above it the LUMO, the lowest unoccupied molecular orbital. You will never need to remember those letters. You just need the garage. Combustion. Every fire you have ever seen is an electron in a fuel molecule's full top floor, finally jumping across into oxygen's empty floor next door. That's it. That's the event. Everything else, the heat, the light, the color, the smoke is the receipt for that jump. Which means, and this is the line school will never get to, activation energy isn't a hill the molecules have to physically climb. It's a toll booth the electrons have to pay to use the bridge between two buildings. Same number, 200 to 400 kilojoules per mole. Completely different picture. Now, full disclosure, I just compressed roughly 80 years of physical chemistry into one parking garage. Real molecular orbitals are more delicate than that. The diagram is a tool, not a photograph. And there are working chemists who would refine almost every word I just said. The picture is honest. It is not the whole portrait, but here's where it gets weird. Because if combustion is an electron falling down off a fuel molecule's top floor, somebody had to put the electron on the top floor in the first place, right? Top floors aren't free. Where did the fuel get its full top floor from? That answer isn't in chemistry either. That answer is outside, somewhere in a tree. Brussels, the 1640s. A doctor named Jan Baptist van Helmont takes 200 pounds of dry soil weighed on a balance, sealed in a pot, and plants a willow sapling in 5 pounds. He covers the pot so nothing else can get in except rainwater. And then he waits. 5 years. When he comes back and weighs the willow, it's 169 pounds 3 ounces, roughly 77 kilograms. The little stick has become a tree. Then he weighs the soil. The soil is still there, almost all of it. He's lost 2 ounces. 2 ounces. Out of 200 pounds, 164 pounds of tree had to come from somewhere. It wasn't the soil. It wasn't the water. He weighed that too. It came from the air. Carbon dioxide that the leaves were pulling in, broken apart, and locked into wood. And the energy to do all that breaking and locking? That came from the sky. Specifically, from photons. Every leaf on that willow was, every daylight second, catching small packets of sunlight, and using each one to do exactly one thing, kick a single electron up onto the top floor of a sugar molecule that didn't have a full top floor yet. That is photosynthesis. Stripped of every diagram you saw in school, a photon arrives, an electron gets parked one floor higher, and the garage we talked about in S5 finally gets its cars back. A log of wood, then, is not really a log of wood. A log of wood is a stack of full top floors, every one of them filled in by a photon, one electron at a time, over years. Full disclosure, real photosynthesis stores at most around 30% of the energy in the photons it catches. In actual leaves, it's much, much lower. The diagram is honest about the direction. It is generous about the efficiency. Now hold these two pictures in your head at the same time. Picture 1. A leaf, 10 years ago. Photons arriving from the sun. Each one parks an electron one floor up top floor of a sugar molecule, then a starch molecule, then a long chain of cellulose. The tree is, quietly, every daylight second, getting taller by saving sunlight as bonds. Picture 2. A match. Tonight, strike it against your kitchen counter, you hold it against a candle wick. The match is not adding energy to the wax. The match is paying the toll booth we talked about in S5. One small bribe, one electron jumps the gap, and the chain reaction starts. And what comes off the candle, the heat you feel on your face, The yellow light you see, the warm air rising, every joule of it was sitting in those bonds, parked there by photons, sometimes years ago, sometimes centuries ago in the case of coal, sometimes hundreds of millions of years ago in the case of natural gas. Fire is not chemistry. Fire is sunlight, a tree stored years ago finally getting back out. Feynman said that, on the BBC, more than 40 years ago. He wasn't doing a metaphor. He meant it, almost literally. The wood in your fireplace is, by mass, mostly carbon and hydrogen that used to be in the air, climbed up onto sugar's top floor by photons, then locked into bonds for a few decades. When you strike that match, you are quite specifically opening the door and letting those photons go home. Yellow part of the flame, blue part of the flame, the heat radiating out, even the smoke carrying away the last bits of carbon that didn't burn. All of it is the receipt for unlocking a stack of photons that have been waiting on a top floor since before you were born. Which raises one more question, and it's the hardest one yet. Does every photon actually have to climb that hill? Or do some of them, every now and then, cheat? So back to that question. Does every electron actually have to climb the hill? Or do some of them, every now and then, cheat? The honest answer is sometimes, yes. And there's an experiment that caught them doing it. That blue glow is a cold flame. Diethyl ether, at around 200 to 300 degrees Celsius, roughly 400 to 570 Fahrenheit. Way too cool to be a real fire. The textbook activation hill we drew earlier says nothing should be happening in there. And yet something is. The glow oscillates. It comes on, dies back, comes on again. Like the molecules are taking turns making the decision. What that tells us is the hill isn't a wall, it's a statistical distribution. Most molecules can't climb it at that temperature, but a few can. 0, 5, beat pause. And a tiny weird minority of hydrogen atoms don't climb it at all. They tunnel. Quantum mechanics lets them, very occasionally, just appear on the other side. No toll paid, no bribe needed. And now I have to be straight with you. Physicists genuinely argue about how much tunneling actually matters in everyday combustion. Conservative estimates say small, but non-zero. Some labs think it's bigger. The picture I just gave you hill as statistical distribution. A few electrons cheating their way through is honest about the direction. It is not the final word. There is no final word yet, which means every flame you've ever watched is, right now, the average of millions of slightly different stories. Some electrons climbed, a handful tunneled, most didn't make it at all. The flame you see is what happens when enough of them, together, do. All right? 11 minutes of invisible electrons making invisible decisions. You're owed something you can actually see. So here it is. Every flame you've ever watched is color-coded, and the color is the decision. Sodium. That's it. That yellow-orange you just saw, that's the same yellow you see in a candle, the same yellow you see in a wooden campfire, the same yellow in an old-style streetlight. Wood has trace sodium in it. Wax has trace sodium in it. The flame's heat kicks a sodium electron from its normal floor up to the floor above. Then, almost instantly, it falls back. And every time it falls, it has to give the energy it borrowed back. It gives it back as a single photon of light. The wavelength of that photon is exactly 589 nanometers, 589 billionths of a meter. That number is yellow, copper, green, different element, different staircase between floors, different gap. Photon comes out green around 510 nanometers. Lithium, red. Smaller gap between the floors it's using. 670 nanometers. Your eye reads that as crimson. 3 elements. 3 different colors. One single mechanism. An electron borrows energy from the heat, climbs one floor, falls back, and the receipt for that climb gets handed to you as visible light. Full disclosure, real atomic emission involves at least 6 quantum numbers, fine structure, and some lines I haven't shown you. I'm compressing all of that into one staircase per element. The colors you just saw are real. The explanation is honest. The full portrait is more detailed than the sketch. And here's the part that should bother you, in a good way. Every flame on Earth, every candle, every campfire, every star is the color it is, because of electrons doing this exact thing, right now, billions of times a second. The yellow of a candle, the blue of a gas stove, the red of Antares. The universe is color-coded by electron decisions, which raises the only question left. If that's what's deciding the color of every flame out there, what's deciding yours? Right now, sitting in your chair, glowing in the infrared? That's me, right now. No flame, no fuel rack, no fire extinguisher in the corner, and that orange light coming off my face, that's infrared. It's the same kind of light coming off the candle we lit 11 minutes ago. Just slower, just lower wattage, just controlled. In 2021, a paper in Science measured the basal metabolic rate of more than 6,000 people. The result is famous now. On average, an adult human at rest burns through about 100 watts of energy. Yours might be 80 if you're small, might be 120 if you're taller. Doesn't matter. The order of magnitude is the same as a bright incandescent light bulb that nobody makes anymore. Inside every cell in your body, there's a chain of molecules whose only job is to walk electrons. Micropause. One at a time from the food you ate this morning. Micropause all the way down to a molecule of oxygen you inhaled 20 seconds ago. Electron in, electron out, down a staircase, step by step, releasing energy at every step, energy that builds your tissue, fires your brain, glows out of your skin in infrared. The last step on that staircase hands the electron to oxygen, just like fire does. Same endpoint, same physics. This is the part I want you to hear cleanly. You are one, running at 100 watts every second of your life. The candle in your kitchen and the cells under your skin are doing the same physical thing, millions of electrons crossing a quantum hill to release sunlight a tree stored years ago. Yours just do it slowly enough to keep you alive, instead of fast enough to burn the room down. That's the only difference. Speed. Containment. Not category. Okay, one small thing to try tonight. It costs nothing, and it'll teach you more than the last 17 minutes did. Find a candle. Light it. Hold your wet fingertip, and I do mean wet. Run it under the tap first, half an inch away from the flame, about 1 centimeter. Don't touch it. I'll say that again. Don't touch the flame. Half an inch away. At that distance, against every instinct you have about fire, you don't burn. It feels warm. It does not blister. Move your finger a few millimeters closer, like 1/10 of an inch closer, and the answer changes immediately. Same flame, same finger, different mechanism. There are 3 mechanisms making that survival possible at 1 centimeter, and only one of them is the one most people would guess. Drop your best mechanism in the comments, not the funniest comment. The best explanation. I'll pin the one that gets it cleanest 24 hours from now. And if you've made it this far, here's the part nobody else gets to say to you, because most channels can't. You are now in the small group of people on the internet who, after watching a video about fire, can explain it at the electron-orbital level without one equation, while staying honest about the parts physicists still argue about. That used to be the whole point of physics, before it became a vibe. This channel is, as far as I can tell, the only intellectual tribe online that asks why before it asks wow. That's not a tagline. That's a sorting hat. If that sentence made your shoulders drop a little, you're already in. Subscribe so the next one gets to you. Comment so I know who I'm talking to. We are not many. That is on purpose. One last thing. If fire is sunlight, a tree stored years ago, and your body is the same, physics running slow, there's one question we haven't gone near yet. Where does the sun get IT from? It's another quantum hill, but this one is 1 billion times taller. The electrons don't just refuse to climb it, they would never climb it. Not in the entire age of the universe. And yet, every second, 4 million tons of hydrogen does. Not by climbing, by cheating. By tunneling, the same way that minority of molecules in the cold flame experiment did, except this time, the cheat is what makes every star possible, and what made you possible, and what put the sunlight inside the tree in the first place. That's the next video. If you want to know how the universe pays a bill it physically cannot afford, I'll see you there. You are a 100 watt slow fire. Stay curious. Next, how the sun pays a bill it can't afford. Press in. Small subscribe under.